Hey everybody, it's Mr. Carr again. Today we're going to be talking about 8-6 day 2. To finish off our rational functions, we are going to talk about a variety of word problems that you're going to see that covers this concept. Okay, so we have a handful of examples. The first one is going to be a mixture problem. So here's our scenario. Aaron adds an 80% brine, which is salt water, solution to 16 ounces of solution that is 10% brine. How much of the solution should be added to create a solution that is 50% brine? So this chart right here is very helpful. Okay, so we're looking at the fact that the amount of brine is being modeled right here. Because it's 16 ounces, that's 10% right now, we can kind of show the amount of brine as being 0.10 times 16. Okay, 10% of that 16 ounces is made up of the salt or the, the salt part. We want to add a certain amount of 80%. So as a decimal number, that's 0.8, we multiply that by x. So the amount of brine is going to be the 0.10 times 16 plus 0.8 times x, whichever that comes out as. Okay. We also look at the total amount of solution. So we started with 16 ounces. We're adding x amount. And in the end, that's going to be the total amount. How this helps us is we're going to set this idea of the problem. The goal is 50%. So we have the percentage of the brine, we remember, is going to be the amount of the brine divided by the total solution. So this is how that looks when we set that up. Okay, so the percent over 100 is equal to the amount of brine out of the total solution. So again, this is going to be the amount of brine. That's the total solution that it's going to be out of. Okay, so that's how I can set this up. The goal is 50% out of 100. And that's going to equal to the amount of brine, which is the 0.10 times 16, added by the 0.8 times x over the 16 plus x. Okay, so amount over the total solution. From here, we're going to treat it like our other rational functions to solve. Okay, my LCD here, if I look at this, it's just going to be 100 times 16 plus x. So as we're going to do, I'm going to multiply both sides by that. So I'm going to multiply by 100, 16 plus x, and then multiply by 100, 16 plus x. Okay, so if I do that to both sides, you notice again, get to cancel out the 100s. So I'm going to have 50 is being multiplied by 16 plus x. Over here, I get to cancel out the 16 plus x. So I'm going to have 100, look more closer to 100, multiplied by 0.10. Well, let me go ahead and just change those right now. 0.10 times 16 is 1.6 plus 0.8x. Okay, so from there, it's just a normal solving problem. We can distribute the 50, distribute the 100. So when I do that, excuse me, I'm going to get, it'll be 800 plus 50x equals 160 plus 80x. Okay, so just like other algebra problems, we'll subtract 50 over and subtract 160 over. So that's gone, that's gone. I get 640 is equal to 30x. And I divide both sides by 30. And after I do that, I'm going to get 21 and 1/3 for my x. Okay, so what this means is that Aaron needs 21 1/3 ounces of the 80% brine. Okay, this is what gives him his 50% overall. So that's a mixture type of problem. So we deal with those percentages. Okay. Another type of problem we have is when we deal with currents in swimming. Okay. So Lilia swims for 5 hours in a stream that has a current of 1 mile per hour. She leaves her dock and swims upstream for 2 miles and then back to her dock. Okay. What is her swimming speed in still water? Okay. So we're going to base this on the fact, excuse me. So basically, we're looking at this as distance equals rate times time. Okay. But what we're going to be modeling is the fact that with her rate changing, her time is distance over rate. Okay. So we actually know the distance here. It's 2 miles. She goes 2 miles upstream and she goes 2 miles downstream. Okay. We also know the total time is 5. So this is basically, if I want to call it two separate things, I could say time upstream plus time downstream is equal to 5. This is right here. That's why I want to use this new formula here. Okay, so we're going to model her time upstream and her time downstream with both of these equations. So that means time going with the current is going to look like this. So since the distance is equal to 2, everything's going to be 2 over r. But with the current, okay, when she's going, sorry, her rate, technically her rate, sorry, I was looking at something else. Her time that going with the current is going to be based on her rate will actually be a little bit slower because she's fighting against the river current. So whatever her rate is, which is r, we're actually going to take this as 2 over r minus 1. Okay, that's the idea of when it's 1 mile per hour is, sorry, 1 mile per hour for the current. So she's swimming against that, it's pulling her back, so it's making her a little bit slower. So that's why her overall rate here is a little bit slower. We're going to add that to her time downstream. Well, when she's going downstream, she's got the water working with her. So her overall speed is actually going to be +2 now. Okay, so again, this is distance divided by rate, but her rate is changing based on, technically I should have done this right over here. Okay, her rate is changing based on how the going with or against the current. And that's going to equal the total time, which is 5. Okay, so what we have here, messed up here, I'm sorry. This should have been r plus 1 with the current, not +2. Okay, so now what we have is this equation. Okay, our distance is, or our overall time of 5 is made up of 2 over r minus 1 and 2 over r plus 1. So just like our other rational functions, let's find our least common denominator, which in this case is r minus 1, r plus 1. So we're going to multiply everything here by r minus 1, r plus 1. Okay, so this one's going to cancel out. I'm going to end up with 2 times r plus 1. R plus 1 cancels out, so I have 2 times r minus 1. And that's equal to 5 times, I'm going to go ahead and just rewrite it as r squared minus 1. Okay, so from there I can go ahead and distribute. So I'll have 2r plus 2 plus 2r minus 2 is equal to 5r squared minus 5. Okay. From there, it's a quadratic now. So with quadratics, we want to make sure we get it equal to 0. So I'm going to go ahead. Well, first thing I can do is I can actually cancel these out. They'll combine to 0. This will be 4r equals 5r squared minus 5. So if I subtract 4r over to both sides, now I can have 0 is equal to 5r squared minus 4r minus 5. Now, this problem actually comes out as a, excuse me, this problem is not going to be a factorable one. It's going to come out as a irrational number. That's what I was looking for. So in that case, I'm going to use quadratic formula. So we could do x equals negative b. So negative with negative 4 plus or minus the square root. Negative 4 squared minus 4 times a times c all over 2 times a. I'll let you go ahead and practice that on your own, simplifying and everything, but you should get out to 2 answers. So when I do this, I get x is about 1.5 and x is about negative 0.7. Now, realistically, because of this, this is, sorry, you know what I should do? I should make these all r's because that's what we solve for. Realistically, since this is the rate of her speed, she is not going to go negative 0.7. So we just get rid of that answer. So what that means is that in still water, got to double check her name again, Lilia can swim about 1.5 miles per hour. Okay. So again, with this setup here, we're modeling time as distance over rate because we know the total time it takes to go up and downstream. But what changes is the rate based on going upstream or downstream. Going upstream, your rate's going to be slower because you're fighting against it, but going downstream, it's going to be faster because you're traveling with the current. Okay, so we're modeling the 2 separate times, but we don't know which each one is, but that's okay because we know in the end it's 5. All right, and I believe, yeah, this should be our last example. and that's going to be this mowing lawn. And this is doing jobs together. Okay, so Wui and Wima mow lawns together. Wui, working alone, can complete a particular job in 4.5 hours, and Wima could complete it alone in 3.7 hours. How long does it take to complete the job when they work together? Okay, so again, we're using the whole, not exactly distance equals rate times time. It's going to be work this time. We can kind of call it work equals rate times time. Okay, so that's what we're looking at here. So if we think about it, work in this case would be like the number of jobs. So they both get one job done. So we can look at their, let's see here, how long does it take them? So we know their times. So we can kind of represent the rate in which they're working by dividing this out by T. So the work divided by T is equal to their rates. So the idea here is that working together, so Wima's rate is going to be 1 over 3.7. Wui's rate is 1 over 4.5. Because again, this is work over time. It's one job in that amount of time that's given. Their combined rate is going to be 1 over X. Okay, this is them working together. So logically speaking, we know it's going to look something like this. Okay, so we're combining their rates together to get to this level. So because of that, we know, here's another thing we also know. We should know the number in the end should come out less than 3.7. Because if Wima can work on mowing one lawn in that amount of time, that means that having a helper should make that time less than that. Like, it's not going to be an average of the two. What it is going to be a number that's smaller than 3.7. Okay, so we're adding this incremental amount that's helping Wima is the idea. So just like before, I'm going to multiply everything by the least common denominator here. Excuse me. So in this case, the least common denominator can just be 3.7 times 4.5. We're not going to worry about trying to see if there's anything smaller than that. We're just going to multiply them together. Because in all honesty, we can just multiply any two numbers together to get a common denominator. So 4.5 times 3.7 gives me 16.65. So that's what we're going to do is multiply everything by that. Okay. Oh, and X. Sorry about that. Because I need to get rid of this X down here as well. Okay. So again, this eliminates all my denominators. In the first case, I've got 16.7 divided by 3.7 is going to 16.65 divided by 3.7 is going to give me 4.5x plus there should be 3.7x, and that's going to equal to 16.65. Okay, so now I can add those together. So I've got 4.5 plus 3.7 gives me 8.2x equals 16.65. And then I'll finish it off by dividing both sides by 8.2. Okay, so 16.65 divided by 8.2. And that comes out to about 2.0305. So what this means, together, if Wima by herself it takes in 3.7, this is their combined rate. Remember, we're representing the amount of work over this rate time here. So X is representing time in this scenario. So together, they can complete the job or complete the mowing in about 2.03 hours. Okay, so again, we're representing each individual rates as work divided by time. So in this case, it was one lawn in 3.7 hours, one lawn in 4.5 hours. We can set that up combined into a combined rate that looks like this, and then we apply our rational function rules to solve it out. Okay, so those are 3 examples. I'm going to show you some more that you can try on your own. So you want to pause the video real quick and try this one out. And then feel free to pause it for this one. And one more to pause it for this one. Okay, but that's it for today. Again, we're just solving our rational functions by using our properties that we've used for other ones. We're just applying them to word problems today. That's all. All right, take care, everybody.